So from our previous examples, we have been defining the derivative of f at some point xi equal to the difference between the following point and the current point divided by our step size plus some remaining error term. So that's what I've written here, that the derivative is equal to f of the difference between f of xi plus 1 minus f of xi divided by our step size plus some error term. Now this is known as the first forward difference, where h here is our step size. So another way of thinking about this is that h is the length of the interval over which our approximation is made. So we've got that, I've drawn that up on this graph here. Why is this called the first forward difference? Well, it really comes down to the fact that we are looking at the next step. So in other words, the derivative at xi depends on the difference between the function value at our next step and current step, and that'll give us our derivative. So we are shooting forward in this instance, hence the name forward difference. Now this is one of many ways that we can approximate our derivative, and we can see now how the Taylor series is becoming more useful to explain to us how we approximate the derivatives of functions in numerical methods. So now we don't actually need to know what the function is, we just need to know functional values at different points. Now the Taylor series can also be used to approximate the derivative from a backward difference approximation as well as a center difference approximation. Now if we look at a backward difference approximation, and we can do that again looking at a graph, and if we plot the function that we're interested, then we calculate this derivative based on the preceding point. So if we want to find the derivative of xi, we look at the preceding point, so we shoot backwards. And this can also be written that f of xi plus 1, so here we're using the Taylor series, is equal to the function value at xi minus the derivative of xi multiplied by h. And you can see that here, so we're shooting backwards. Now, to calculate the value at f of xi minus 1, we can then, we can use the Taylor series, as I've already mentioned. Now we can approximate the derivative of our function by rearranging this Taylor series to get that the derivative using the backward difference method is equal to the difference between at xi, so f at xi minus f at xi minus 1 divided by h plus our error term. Now, as I've already mentioned several times, this is known as our backward approximation of the derivative. Now, there's another way that we can do this. We can actually calculate the approximate value of our derivative by using a centered approach. Now, in order to do that, we need to, so let's just draw it on this graph. So we can actually just extend our graph to x of I plus 1. So we can actually use the function value of xi plus 1 and the function value of xi minus 1 centered about xi to give us a better approximation. So really what we do is we subtract the backward difference from the forward difference, and we then rearrange our function, our Taylor series. So I've already written that here. So the difference between the forward and the backward method gives us that f at xi plus 1 is equal to f of xi minus 1 plus 2 times f of the derivative at xi plus an order that is proportional to h squared. Now, why does this happen? Well, if we go back to the our previous method, so here we have the backward difference, we see that the error terms from the backward and forward cancel out, and we actually left with the third order or higher order terms. So we can say the remainder is actually equal to the third derivative of the function value multiplied by the cube of our step size, and that all divided by 3 factorial. And obviously when we then divide by h to rearrange our derivative, so the derivative about xi using the center difference approach is equal to the difference between our next point and our preceding point divided by twice our step size plus an error term that is proportional to h squared. Now this is really important because it means that our approximation is much more accurate. So let's look at this at a bit more detail in our next example.